So do you have the screen?
Yes.
Yes.
Okay.
Go ahead.
Okay, so just I want to do some. Okay. Okay. Thanks everybody for joining my presentation here. I hope everyone is safe and is doing well today. So I will start to start my presentation here. So my topic for PhD was structural performance and occupant response in Cutaway bus rollover crash. So for this presentation, first I will talk about rollover and the characteristics of this type of accident and what are the safety issues for the buses. And then I will give you a little bit of information about what's the current status of the occupant response and the safety of the rollover crash for the bus. And then I will start with the experimental study that we conducted for using two different test methods and then with the same occupant configuration and how we use that data to develop our finite element model in the next part. So in the finite element analysis section, I will go through the details of the FE model and how we develop those models to do some parametric study. And then I will finally give the details of the accident reconstruction method that we use. So we develop a new numerical model based on the multi-body dynamics, and then we try to reconstruct the accident and integrate that with our finite element simulation. And then finally, I will go over the summary, limitations, and the research findings of my dissertation. So without further ado, let's start with the introduction. So rollover crashes have the highest fatality rate. So for example, in 2015 in the United States, there were only 3% of all accidents, but more than 35% of all deaths were because of the rollover accident. And they're usually multi-directional, which means that they have rotational and linear acceleration and velocities, and they are associated with multiple impacts, which create a complex deformation and also complex interaction between the occupants and structural component. And they are predominantly a single layer crash, and also depends on which phase of the study, we can divide the accident, rollover accident, like other type of accident, into pre-crash, crash, and post-crash phase. And you can see certain goals are followed based on the phases that we were studying. For example, in pre-crash, we follow the injury prevention and try to prevent the accident. In crash phase, we try to mitigate the injuries and reduce the injuries. And in post-crash, we do follow the injury care. So why bus rollover crashes? So in the first look, we see that bus rollover crashes are one of the most frequent cause of the mass casualty. And then in the first look, as I said, they are low probability event, but at the same time, they have the high consequences. This means that, for example, one bus rollover crash can cause several fatalities, which is equal to a couple of passenger car rollovers. So we can't ignore them because they are rare events. And available experimental and numerical studies were focused mostly on the structural integrity, and they didn't consider the occupant response in that. And also available field data analysis or statistical analysis look mainly on the post-crash data, and they try to just show the injury outcomes that caused by the accident. And we don't have a clear picture and clear information about what exactly occurred to the occupants during the rollover and what is the interaction between the occupant and what's the source of those injuries. So for the rollover crash, the big difference between the rollover crash and other type of crashes is the time, because rollover crash occurs more than a second, but the other type of crash, such as side impact or frontal crash, usually happens over a millisecond. So we have to divide the rollover crash phases into sub-phases to kind of do some analysis. So as you can see here, the crash phase is divided into tripping phase, airborne phase, and first roof to ground impact phase until the rest position. And from tripping phase to rest position, the bus can roll on only one quarter turn, or we can have several revolutions. And like other type of accidents, we have several factors that are contributed. So vehicle, human, environmental factors, and their interactions. And the occupant protection system here during the crash is try to control the human and structural interaction. And similar to other studies, we have three different main methods to address the safety issues: experimental, computational, and statistical. And I will explain about these methods and how we can use those to address some of the safety issues. So being that said, let's start. What are the Cutaway buses? So Cutaway buses are mostly manufactured in the United States, and they are manufactured by two different companies. So for example, the driver cab and the chassis is manufactured by vehicle companies such as Ford or General Motors, and the passenger compartment and the seats inside are manufactured by local companies. And also, they are designed to transport up to 22% passengers. Um, so for the bus rollover safety, we don't have a regulation in the United States, but in Europe, the main regulation is the T-table test. And we have also FMVSS 220 with strength test and also the modified rollover test that are currently used to do for the rollover crash safety. So among them, you can see the T-table test is the most widely used because it's a regulation in Europe, and manufacturers use that to prove their safety or structural integrity. The roof strength test, the research shows that it cannot reflect the real world impact condition because it applies the vertical load to the roof, which I will show you later how it's different from the normal or usual bus rollover crash. And the big question about modified rollover test is repeatability, because it's very hard to have the same vehicle kinematics, even using the same vehicle, the same bus for two tests. So being that said, let's talk about a little bit about the occupant response and what is the current what research has been done so far to address the occupant response in the literature. So you can see here, most of the studies are numerical study, and we don't have an experimental study about the occupant response and occupant interaction with the passenger compartment for the bus during the rollover. And these numerical studies have used different human model using a simplified structural model, which they call it the base section of the bus, and they use only the T-table test to address the kinematic of the occupant. And in none of those studies, they use the experimental data to validate the occupant response. So we don't have a clear picture about what exactly happened during those tests for the occupant, and we saw some discrepancies in the literature. So for the introduction part, I was able to publish a literature review paper in the Crashworthiness Journal, and this paper was not about only the bus rollover crash, it was about the passenger car rollover crashes, because they had the same concerns, but with different, a little bit like different mechanism. So the research objectives for my dissertation, first, I was trying to quantify the kinematics of the occupant and also the vehicle in different impact conditions that caused by the rollover, to address some of the issues, like what are the most common type of the injuries and what are their severity. And then find the source of those injuries and see how the effectiveness of the restraint system on injury prevention. And the second goal is to characterize the available bus rollover crash tests in terms of how well they can address those issues. Because it's very important to look at those tests, the current tests, to see how they can address and how we can address the occupant response. and then identify the possible relationship between the structural strength and injury outcome, and finally do some analysis, evaluate the vehicle and occupant response in real-world rollover crash to have a kind of more realistic analysis and see how those tests and how our research can address the real-world safety issues that we face for bus rollover crashes. So let's start with the experimental study. But before that, since we use these two terms, vehicle response and occupant response, many times over this presentation, I need to be clear here. So the vehicle response, what I mean by vehicle response is the measurements of the bus center of the gravity in terms of the acceleration and angular velocity. So for the experiment, we use accelerometer and the gyro to measure that, and also the structural deformation that we measure the deformation of the passenger compartment in two different sections. And what I mean by occupant response, which we use the anthropomorphic test device to capture the kinematics of the occupant, is measuring the acceleration of the head, chest, and pelvis, and also the force moment measurements for the upper and lower neck. So with having those, we can calculate the injury criteria. So these injury criteria that you can see here are defined, they are well-defined injury criteria. So based on the kinematics measurement, we can calculate the injury criteria and then compare them with the human tolerance to measure the injury risk for different part of the body. So let's start with the experimental test. We use the two rollover mechanism, the T-table test and the modified Dolly rollover test, which I would say an MDR test. So for the T-table test, we put the bus on the table 800 millimeter above the ground, and the table is slowly tilted less than 4 degrees per second until it will reach the point of unstable equilibrium position, and then it will fall under its own weight on the flat concrete surface. And for the MDR test, we do have a vehicle that we put it on the cart, and the cart is 140 millimeter above the ground, and the cart will move laterally until it will reach the 25 mile per hour, which is equal to 11.2 meter per second. And then it will suddenly stop, and the bus will release from the cart, and it will roll over on the concrete surface. So for preparing the test, we have to measure the center of the gravity in two different conditions: the loaded and unloaded. For the loaded case, we put these water balloons to replicate and mimic the occupant weights, and we use the same bus, the same model for running these two tests. And you can see from this table the numbers are pretty equal for the same bus for both loaded and unloaded. So the center of the gravity that we measured is similar on both bus for these two tests. So here is the occupant configuration that we use, and they are the same. So we use the hybrid 3 dummy or ATD. In the first row, you can see the 2-point belted dummy that we put in the first seat row. And the second seat row, we have the 3-point belted ATD, which they call ATD3 and ATD2. So we had the same occupant configuration in both MDR test and T-table test. And here you can see the gyroscope and accelerometer that we mounted at the center of the gravity. And we have 8 transducers that we put in the front section and the back section to measure the structural deformation. And you can see here the location of the cameras. We put several cameras inside and outside the bus to capture the movement of the occupant and also to capture the vehicle motion. And here is the overall picture of the MDR test. And also the concrete surface for the MDR test, we can see how is the surface, which is the friction is around 0.8 for this experiment. For the data analysis, all of the data from the vehicle were collected at the 20 kilohertz frequency rate, and we have to pass the data into from the certain filters based on according to the SAE J211. For example, for the gyro, we have to pass the data from CFC channel 60, and for the accelerometer, we use the 180 CFC filter. And to have a more meaningful data or results from the accelerometer, we have to transform the data from body fixed coordinate to the earth fixed coordinate. So for that, we use the quaternion method. And this line here, you can see that's why we were able to track the location of the COG during the whole time of the MDR test. So here in this video, you will see the overall motion of the bus during the MDR test and also the resulted roll rate and resultant acceleration for the bus. So for this test, the bus experienced around 270 degrees per second roll rate and around 15 G for the resultant acceleration. And you can see the bus had several revolutions until it will reach the rest position. And here is the same, as I said, same occupant configuration, but for the T-table test. So for this test, the maximum roll rate was around 160, which was around half of the value that the bus experienced during the MDR test. And the maximum acceleration was around 7G. And here is the summary of the results. So as we expected, the value of the acceleration in MDR test was much higher. And also the roll rate in MDR test was significantly higher. But unfortunately, we were not able to capture and measure all the data for the structural deformation, and we had it only for one section, which is also important because this section, the front left section, was the place that we put two dummies here, and you can see the value for the T-table test was higher than the value that we observed in the MDR test. So the DI is the index that we use to show the deformation of the passenger compartment. The DI more than 1 means that the passenger compartment intruded into the safety space, and the DI between the 0 and 1 is, which means that we don't have any intrusion. So the maximum height of the center of the gravity above the ground for the T-table test was 2.6 meters above the ground and 2.8 for the MDR test. And the roll distance, which is from the starting point to the rest position, for sure for the MDR test was around 15 and 1.5 for the T-table test. So the one thing that we need to look at it for the experimental test is the energy distribution and how energy dissipated through these two experimental. So as we can see here in those graphs, the initial mechanical energy for the MDR test was significantly higher, but at the same time, the structural deformation that we observed for the MDR test was lower than the T-table test. The main reason is, I think, and we saw that is the total energy loss for the MDR test was equal to around 300, which was mostly dissipated during the tire to ground impact contact. But on the other hand, for the T-table test, most of the energy loss was because of the impact between the passenger compartment and the ground. So that's why we observed more structural deformation for the T-table test. And what we mean here by a mechanical energy, here you can see the equation. The rotational kinetic energy and translational kinetic energy is the mechanical energy, and we do have a potential energy by calculating the height of the center of the gravity, and the total energy is the summation of the whole energy here. So let's look at the occupant and how occupants moved and what are the kinematics of the occupant. So here is the video of the inside of the bus during the MDR test. So the third ATD is uninstrumented and it's unbelted, just to show if you don't use the seatbelt, what will happen and how you will move during inside the bus. But as you can see here, we do have the side window will fail and shatter, and the first ATD and the second ATD will remain in their seat. But I will show you later how we do have a partial ejection during the last impact for the first ATD, or ATD2, which was belted by 2-point seatbelt. And here is the occupant position at different moments. So we can probably see, for example, here how the upper body part of the ATD moves inside the bus and how we have some impacts between the interior compartment and also the ATD part. So that's why we were able to synchronize the video data and also the kinematic data that we have and try to understand why the reasons for the peaks. So here in this graph, you can see the head acceleration for the 2-point belted dummy. And because we used the painted bodies and painted head, we were able to track the contact points. And these first 2 peaks were because we had an impact between the head and the window frame. But the last one, which is the significant, is because we had a direct impact between the head and ground. So due to the partial ejection. So here we can clearly see that what was the cause of those kinematic responses. And here is the results for the T-table test. For the T-table test, we had very similar occupant response for both ATDs, the 2-point belted and the 3-point belted ATD, because we didn't see any major partial ejection, and also the most of the data from the head acceleration and also chest and pelvis were very close, and I will summarize them in the next slide. But you can see here, even though we had some impacts, for example, here between the head and window frame, but the results were not as high as what we have seen in MDR test. So here we normalize the injuries. So what I mean by normalize injuries is then after we calculating the injury criteria for each part, we use the injury assessment reference value to which they are certain numbers. So we normalize them based on the human tolerance that we have from this method, and then the higher the number is, the level of the injury is higher. So for example, in the MDR test, you can see the values for the 2-point belted, which are the red one, are significantly higher compared to the 3-point belted dummy, especially for the head and chest. And for the T-table test, you can see the difference between the 2-point belted and 3-point belted was not much, and we had the similar kinematic responses. And the other point is we can quantify the effectiveness of the 3-point belted. So here, the 3-point seatbelt reduced the risk of the head injury around 80%. And unfortunately, we didn't have also the results for the chest for the 3-point belted dummy. So here is the summary and the response for the 2-point belted and 3-point belted, as I said, for the T-table test were very close. So all of these experimental data we were able to publish all of this data in the accident analysis and prevention, which we provide promising data about the kinematics of the occupant and bus during the 2 experimental tests. So let's go to the finite element analysis and how we develop the finite element model. So the finite element model we developed in using the LS99 Hypermesh software. And we use the available ATD model, and we only model the seatbelt, the 2-point belted seatbelt to restrain the ATD. And as you can see here, the full FE model contains 8 submodels such as skin, entrance door, side window, seats, steel structure, and chassis. The data for material and connection characteristics we used the data from our previous models, but we did further validation to have a more solid and accurate model to do some parametric study. So to do the validation, we use the correlation and analysis software. So this is the free software that we that compare two curves from different using two different methods. So the cross correlation rating and corridor rating, and it will compare the phase, size, and shape of two graphs, and it will give us a rate based on how well these two curves are correlated. So the number between 6.5 to 8.6 is good correlation, and the number between 8.6 to 10 is indicate the excellent correlation between the two curves. So let's start with the vehicle response and how we develop the model. So here is the qualitative and quantitative comparison between the MDR test from experiment and our numerical model. So for each simulation, which took around 3 seconds, for example, if we use 200 processors, it will take around 4 days without using ATDs and putting ATDs inside the bus. And the overall results and the data shows us that this model can well replicate the physical model that we observe from the experiment. So here, this was the part that had the most energy dissipation from the tire contact to the ground, contact between the tire and ground. So, and here is the comparison between the experimental and numerical results for the velocity in two directions. So the results show we had a good correlation, but I will show you the Cora rate result also further in the next slide. And here is the simulation of the bus during the t-table test. So the t equal to 0, the simulation starts when the bus starts to fall under its own weight, and the overall simulation took around 1.5 seconds. So with these two models, the Cora rate that we calculated from the comparison between the experiment and numerical, we had 0.7 and 0.9, which indicate a good and excellent correlation for two different results that we get from the two experiments, which shows us that we can, and we are confident that it will replicate the overall motion and vehicle response in our model. And from the Occupant perspective, which we try to validate the data that we have from the experiment, here you can see the results of the t-table test, and from the simulation and experiment, the overall rates indicate that we will have a good correlation from the quantitative assessment. But here also we compare the qualitative assessment or motion of the ATD inside the bus at different time moment. So you can see even the movement of the ATD is very similar to what we have observed in the experiment. So we are confident that this model we can rely the results for this model from this model to do some parametric study. Therefore, we conducted a parametric study using selecting different parameters. The first important part is, since the bus rollover, even the results that we extracted from the t-table and MDR test shows us the lateral load is the dominant impact mechanism during the t-table and also the other test. We try to use another type of dummy to see how what is the difference between the hybrid tree, because hybrid tree is originally designed for the frontal crash, but the Euro SID here that we use is originated and designed for the capturing the occupant kinematics during the side impact. And then, since we want to see the effects of the partial ejection, we use the bus with and without side window, because failure mechanism simulation is very hard, and we can't put the window and try to simulate the failure of the window. So we have two cases, with and without side window, just to see how partial ejection could affect the injury outcome. And then we also use the two friction values for the impact surface to see how it will affect the passenger structural deformation. So with that, here you can see the FE simulation matrix. And so here you can see the two HD dynamics. I need to mute some. So here you can see the FE simulation matrix here from two different ATDs with two different frictions and different type of side windows that we use. So here is the results for EuroSID for two different conditions, with side window, which is the left picture, and the right one is the without side window. Of course, we had a partial ejection here, and you can see the upper part of the body for the EuroSID is completely ejected from the bus. And we had a significant difference between the kinematic response. For example, here you can see the head acceleration for the case that we had a partial ejection was around 350, and without the partial ejection, it was around 20. And the same results that we observed for the hybrid 3 ATD, which we did have a partial ejection for the case that we didn't have a side window, and we didn't have any any significant impact when the occupant remained inside the bus. But we also observed a difference between the results. The main part was the ejection mechanism. So as you can see here, for the EuroSID, since we don't have a full hand model, the whole part of the body went out of the bus, and we had a direct impact with different angle with the ground. But for the hybrid 3, you can see the left hand stuck between the sidewall and the ATD's body. So the partial ejection mechanism was different. So therefore, we saw a different neck injury risk for these two that was predicted by these two ATDs. So for example, for the EuroSID, neck injury risk was much lower. The ones that we saw and predicted by the hybrid 3 ATD. But all in all, the result shows that whenever we had a partial ejection, the risk of the injuries for head and neck was significantly high. And in all of those cases, the pelvis injury, the risk of the pelvis injury was very low. And the other point was using different friction surface didn't change the structural deformation, at least for these two numbers that we simulate. So we had the same vehicle response for all the simulations. The numbers were very similar. So for the results for this simulation, I was able to publish one paper in Journal of Automobile Engineering, which we provided data from this FE analysis. And I was also attended to different conferences to present some of these results. So let's go to the last part. So the accident reconstruction. So as I mentioned early in the introduction, we have three different methods: statistical, experimental, and computational analysis. So to better understand the rollover mechanism and injury mechanism during the rollover crash, it's better to have a multifaceted approach that considers the feedback from other systems. And for example, we do need to have some feedbacks from what happened in the real world crashes, and then try to replicate them in our experiment or numerical analysis. And since we don't have much data about the bus rollover crashes, we started to do some accident reconstruction. And accident reconstruction using finite element model is very computationally expensive. So we have to have a new model to do the accident reconstruction, and then integrated that with the LS dynamic. So the process here is we first try to replicate a real world accident based on the data or based on the reports that we found from the real data, and then try to simulate and reconstruct the whole accident, and then use the results of the accident reconstruction to build the FE simulation and use the initial condition that we extracted from the PC crash simulation to simulate the first roof to ground impact. So I will show you in a detail in a next slide. But before explaining the more details, we need to go through the PC crash simulation. So the PC crash simulation is based on the multi-body dynamic analysis, or based on the multi-body dynamic and also single rigid body. So the mathematical model here is the equation of the motions for 14 degrees of the freedom. And the method that they use to solve this equation is a discrete kinetic time forward model. There are two main parts for the PC crash simulation: the vehicle model and also the impact model. And there are several options that we can use, but according to the literature and technical manual, for the rollover crash, it's better to use the sliding impact mechanism, since you have the 3D meshes of the vehicle. It will define the contact based on these 3D meshes that we see here. And the vehicle by itself on the right side, you can see here, it's just for the visualization, but the contacts and the transfer of the force are applied through these meshes that we see here. And we do have certain assumptions for the PC crash. For example, the contact between the tire and ground is only 1 point, and we do have a zero spring displacement for the vehicle in the statistic position. And for the tire model, we use the simplified mathematical model, which is known as TMEZ method. So with having that, we try to replicate the MDR test using the PC crash model. So as you can see here, the overall motion of the bus was very similar to what we have seen in the experimental test. Of course, we can't have the like a very close data with the experiment, because this is very simplified model, and it has only, and it used a single rigid body, so we don't have a structural deformation for the simulation. And so here, with this one, and also with the results of here comparison between the kinetic energy, we saw that in none of those simulations, such as FE analysis and PC crash simulation, we didn't simulate this part, which we had an impact between the edge of the concrete and the bus. So therefore, the results were a little bit different, especially for this part, from our numerical simulations and also the experiment. But overall, it shows us a good correlation, so we can use that to do some accident reconstruction and use it in our analysis. So let's talk about the procedure, how I use this PC crash model to do the accident reconstruction. So first, I have two full details of the accident report from rural area and urban area. So these accident reports have complete information about the vehicle, road, and occupant details, and even the the velocity of the vehicle prior to the crash, which they extracted from the EDR system. And also we do have a structural also deformation. So we try to reconstruct those accidents based on the evidences that we have in the accident report. And then there are certain built-in functions in the PC crash that we can use to find the optimal values for the impact parameters using different optimization method. But here we use the Monte Carlo to find the optimal value, for example, for the impact angle and also the friction between the two vehicles. And then we extract the data from the bus series to put them as an initial condition for our final analysis. For the next part, we do also have the two results from the T-table test and modified rollover test. And then we are also conducted the final element analysis using the data that we extracted from real world accident, we added the same ATD with the same configuration to compare all of those results, and then we have the results and we compare them based on the occupant response and the vehicle response. So here is the last part. So you can see how we kind of integrated finite element model and our PC crash simulation. So here is the results for the first accident simulation and reconstruction. So you can see here we need to, excuse me. Okay, excuse me. So here you can see. So let's see how. Okay. So here you can see we have the initial condition of the vehicle that we extracted from the airborne phase at the 2 equal to 2.6 to have that as an initial condition for our finite element analysis. So we have the vehicle kinematics for both vehicle, especially for both vehicle, and so you can see there. Here is the results for linear velocity, acceleration, angular velocity, and angle of the vehicle during the crash. And then we use the data at t equal to 2.6 second to and set it as an initial condition for our finite element analysis. So here is for the first case, and here is the results for the second simulation of the accident reconstruction. So the velocity here was for the truck was 6.5 meter per second, and for the bus was around 9 meters per second. And we did the same. We captured the moment that the air going to start, and then we extract the data of this bus COG from the curves at t equal to 3 seconds, and then put it as initial condition of the finite element simulation. So finally, we will have we will have a 4 simulations, which you can see here. So the 2 real-world accidents, which are on the right side, and the 2 tests that we had here. This picture only shows the impact force that we had between the vehicle and ground. So with comparison of all those forces, you can see here the maximum force that we observed was during the MDR test, but it was the contact between the tire to ground. But compared to other tests, the T-table test provided a higher impact force compared even to other accident reconstructions that we had. So the maximum impactful force was around 250 kilonewton, which was produced in the T-table test. So here is the comparison of the vehicle, and also here you can see the structural deformation that resulted in all of those rollover scenarios. So the maximum, as we expected, since we had the maximum impact force for the T-table test, the T-table test showed the maximum structural deformation. And also the point was that the maximum deformation usually occurs in this part of the car structural component, which they call it cantrail. So we don't have a vertical deformation, which I showed you the one test that we had, the FMVSS 220, that they just put a vertical force to measure the structural strength. So most of the deformation was at this point cantrail, and in none of those rollover scenarios we had the DI or intrusion between the passenger compartment and safety space, but we had this different injury outcome, which I can show you here. So in between all of those scenarios, the MDR test provided the high level of the injuries, and the ATD predicted the high level of injuries for that rollover scenario. And but in none of those other rollover scenarios, we had a significant level of the injuries. So, and finally, the bus deformation was not identified as a source of injury in any of those crashes. So being that said, I think I explained all of the simulations and experiment that I experienced, that I conducted during my dissertation. And the results for this part, we submitted a paper and it's under review in the Journal of Safety Research. We planned to attend to 2 conferences, which one of them was canceled and one of them was postponed due to this current situation. But we also had one conference paper in conference in the SAEM conference. So yeah, let's go to the summary, limitation, and the research finding. So in my dissertation, first I conducted we conducted 2 experimental rollover crashes, and then we developed a finite element and a model of the bus and ATD and validate the results to have a better understanding what exactly happened during the different crash scenarios. And then we quantify the kinematic responses of 2 different ATDs and different impact conditions. And then we developed the dynamic model of the bus and PC crash to reconstruct 2 different accidents, real-world accident, to have a better understanding, to have a more realistic assessment of our, say, bus rollover safety. And then we were able to have kind of a feedback from different analyses. So as I show you, I call this triangle safety research. So we had the results from accident reconstruction, and also we had the results from full-size test experiment. And we used 2 different numerical analyses to have a better understanding of what happened to the occupant and vehicle during the bus rollover crash. Of course, we had some limitations in our study. The more important part is the ATD, or the dummy that we use in our model, is originated for the frontal crash, and we don't have any original dummy or ATD that is developed for the rollover crash. So we have to use the hybrid 3 ATD to capture the injuries, to predict the injuries. And then maybe different bus superstructure could lead to the different deformation and occupant responses. And the other limitation was about the real world data, crash data, that we didn't have much information from the outside. And to summarize my research findings, so as I mentioned, using the FE model of the ATDs, we were able to see that the high risk of the injury is for the head and thorax when we have a partial ejection. The T-table test, we could say that it will provide the highest impact force to the passenger compartment. However, the MDR test showed the highest injury risk for the occupant. The minimum injury risk was for the pelvis, and comparison between the 2-point belted and 3-point belted seat belt, we can see the lab seat belt is not effective to prevent the occupant from partial ejection and severe injuries. And the last one was the intrusion of the passenger compartment, which, unlike the passenger cars, the structural deformation is not identified as a source of any major injuries. So the future works some of the studies that we didn't do in our research first is to see the occupant body posture. So different posture may cause different injury outcome, or different side window characteristics can lead to the different injury outcomes, and also the seat position inside the bus. The other thing is we only use the ATD, the male ATD, which we can use we do the injury assessment using the female ATDs. And the last one is, since our analysis was kind of a deterministic analysis, we could do some stochastic analysis using these high fidelity models, but it will be very computationally expensive. And finally, first and foremost, I need to thank Dr. Jung for the support and advice and inspiration for my PhD. And then I definitely need to thank Jeff and Dr. Wekezer for assisting me during my PhD and helping me for all of the studies that I conducted in my dissertation. And also, I'm grateful to appreciate the financial support from the Florida Department of Transportation, which sponsored the project, my project. And being that said, I think I'm almost done. Here is the list of the peer review journal. So far, I had 3 papers and one is under review. And I have around 6 conference papers. And here is the list of the reference. And thank you so much, everyone, for attending and joining me to this presentation. So let me know if you have any questions.
Thank you, Reza.
Oh, no problem.
All right, I will first open the floor for the visitors to this seminar. I will then go to closed room discussions, which will be only for the committee members. So those who are visiting virtually, do you have any questions or comments for Reza?
I need to say that thanks to the Zoom, I was able to have some friends from different countries, from Italy and also Sweden, I think.
Oh, I see.
Yeah,
Wow.
so I hope everyone is safe before, but please let me know if you have any questions.
All right, if
Comment.
not,
I have a
go
comment.
ahead.
This is Seirvogel. I have a comment.
Oh, yeah.
I think I like your very important conclusion at the end, that the formation index is not the major source of the injury, that we have the other things. Because under the old approach, we might be able to create something like tanks instead of the buses. But would this help in mitigating the injury? Probably not. So I believe that your comment is very important. The conclusion is very important.
Thank you. Yeah.
Thank you.
Yeah, thank you. That's right. So it was one of the things that we work on it and we published in a one paper.
Right.
I hope I wasn't very fast in my presentation.
Yeah, Jerry, thank you for allowing me to join you. I joined this opportunity about 3 or 4 years ago when Jerry was transitioning to the retirement. And the relationship that Jerry strengthened with FDOT Transit Office, we were able to continue this. And a lot of the testing was impossible without Jeff Seirvogel. So I want to recognize him also greatly.
Oh,
but this testing was, I'm proud to say, the first ever in the world. And that's because of that combination of people and generous support from Florida DOT Transit Office. So we're very excited that we are the first one to test the nearly identical buses in 2 different experimental conditions. And that will be really informative to other people. So we're very excited about that.
that's true.
If visitors do not have any other comments, I need to ask you to please leave, and committee members need to stay for closed room discussions. So if you're visiting, please leave from the presentation.
So I'm leaving.
Thank you all to the guests who came. That's awesome.
Yep.
Thank you.
Thank you, Reza.
Oh, thank you, Hossein, for joining us.
Jerry's good. Oh, he's gone.
Yeah.
Very good job.
Yeah.
And XT1585, whoever he or she is.
Okay.
Okay, so let's see. We have now committee members only. Great. All right, now we're getting into closed room discussions by the committee members.
But can I ask, before asking a question, if Dr. Maxim can turn his video on? I want to just take a picture just to have it.
Oh yeah, I see. Yeah.
I want to
Oh shoot, I didn't dress up, sorry.
No, it's okay, it's okay. I want to just,
Normally I am better dressed, but
I don't know, Dr. Maxim, if you can turn your video on.
can you, so that he can take a photo of us attending?
Yeah, I will get a screenshot from my window because
I'm not joining the video because my computer is having issues with the audio. If I start including.
Okay, so I have your picture. Okay, so I'll just take some. If you just look at the screen, I'll just take some of the screenshot. Okay, great. I think I did.
Wow, that's cool. Picture taking with the committee members.
Yeah.
With the Corona head.
What a world we are living in.
Yeah, exactly.
All right. Comments, questions, committee members?
I have some questions. I'll start. Reza, great job. I think this is a great area of study, and it's good to see that you are continuing the excellent research in this area. I would encourage both you and Dr. Jung, that clip where you've got the finite element bus and the real bus rolling. It is amazing the high degree of correlation and the visual impact of that. I would love to see just that clip kind of rolling on those screens in the atrium once we get back in the building, with, like a little caption, referencing the project and some kind of easily accessible words about what it's describing. I think that would be fabulous.
Yeah, I think we had one. I think it was open door house.
Yeah. Open house.
Open house that we showed some of the videos. But yeah, I would love to show my
That's
results.
wonderful.
Yeah, we need to create a advertisement kind of video. And these accidents, they occur once a while. Whenever they occur, easily over 10 people die.
Right.
Altogether. So.
And I remember back when Jerry was running it, getting a commendation about some of the work that he had done in recommending, stiffening of the frame of the buses. So
right.
I think it's just really neat and visual. I think it would sell really well.
Also, what's good is at least the Florida DOT Transit Director is very visionary. That if you're riding one of those smaller buses in Florida, you're much safer than other buses in other states, because they actually pay attention to the safety. Because this is not yet federally regulated, it's up to the state. So if you go to other states, riding in these buses are not really safe, whereas here it's a lot safer.
Right. Well, so my question was going to concern the accident reconstruction portion, and I have kind of a couple of questions about that. Yep. But you focused on a couple of crashes that resulted from side impact first.
Yes.
And then there was a rollover.
Yes.
What was your thinking when you decided those? Was it based on the frequency of the type of rollover crash? Because I would think that would add additional complexity compared to, say, a run off the road single vehicle rollover.
Oh yeah, that's right. So our limitation was the accident reports. So the source that we used for the reconstruction was the NHTSA report. So they don't have all data or reports from different accidents. So when we look at the data, we were able just to see these two cases that was the most representative one to our cases, the model that we had. And we didn't have any other option. So I searched a lot in different sources, but these were the only tests that the reports that we had with the full details. We do have some other accidents, but they didn't have any details of the accident.
Okay.
So this was the only reason. But yeah, and also about the side impact, which both of them started from the side impact. Yeah, that's very true. If we want to do the finite element simulation, we probably can capture that part too. So we can start the finite element simulation not at the beginning of the first roof to the ground impact. We can start from the side impact, but it needs to have the other finite element model of the other vehicle to have the full simulation. So it will take a lot of time. So, but this is something that we probably need to look at it too, for sure. Yeah.
Well, you answered a couple of my questions in that series, but one thing you mentioned is that you got the vehicle velocity.
Yes, from the
Can you tell me
EDR.
more about that?
Yes, we had the vehicle velocity from the accident reports. So they pull up the information from the EDR system. So
Is
they
that like a
had,
black box?
yes, yes. So they had the data even prior to the crash.
Okay.
Yeah.
Okay. So I was going to recommend to the team in general that if there is a fatality, a lot of times the local law enforcement agency will do a more detailed accident reconstruction. So it's not just the rollover case or the whatever, it's if there's a fatality, they go into more detail with it. So that might be an opportunity to get a better, more expert reconstruction rather than just the first responding law enforcement officer. But I think you would probably have to go to one of the local law enforcement agencies or the Florida Highway Patrol, because I'm not sure that that data makes it all the way up into like the HSMV and FDOT crash repositories. That's just that very tabular data that's on the initial crash report. So that might be a direction to go if you wanted to continue in this direction of the accident reconstruction.
Yeah, yeah, sure. Thank you.
Okay. And one other question that's just kind of a follow-up in general. Do you all know if any of these conferences that are getting canceled, are they going to publish the proceedings electronically, or is it just gone?
From the two conferences that we plan to attend, one of them turned to be virtual, which we tried to not participate. The other one was just postponed for the next year. So we will present our presentation next year. So
Okay.
there was no cancellation for that.
Yeah.
Yeah.
Okay. Yeah, that's what I was curious about.
Yeah.
Okay, thank you. I'll mute myself and listen to the others.
Yeah, thank you. So,
can I ask a high-level question?
yeah, sure.
So you presented a lot of really nice, really interesting results. What I was wondering if you could summarize for me, sort of in your own words, what the contributions of your thesis are. So this is not the same thing as the results you got, but what do you think are the high-level things that you've done that have increased the body of knowledge of the world? For example, Dr. Jung mentioned at the end of your presentation that this was the first time that we'd gotten results from two almost simultaneous similar vehicles, different types of experimental, and compared the two. Yes. That seems to me like a significant contribution that I didn't see in your presentation. So what other things, what would you classify as the top contributions?
Yeah, so beside what Dr. Jung mentioned, that's for sure one of the things. And as I mentioned in the introduction, from what I studied over the literature review, we didn't have any kind of study, biomechanical study of the occupant inside the bus using the validated experimental data. Okay. So the first part was the validation part, because in none of the numerical study for the biomechanical, at least for the occupant bus, there was no validation and no human model that they can trust to analyze the data. So adding those data and adding those model, validated model, give us confidence that this is the first, I think, study by itself to have the validated numerical model and represent the details of the occupant response based on the validated that comes from the experiment. So that was the other part of my research. And so yeah, these two, I think, was the main contribution of my dissertation, if I want to highlight them.
Okay. Usually when I'm reading dissertations, I like to see a list at the end of the introduction section where you list these contributions. It's good to have top two. There's probably more. My second question is, are there any recommendations that you would feel comfortable making now to improve the safety based on the analysis that you have done? You know, I think it's obvious that wearing a 3-point seatbelt is better than not wearing a seatbelt. But what more could you say in terms of like recommendations for improving safety going forward?
Yeah, when it comes to the recommendation, I think you're talking about like if we want to do some regulations for the safety. So
Design, procedures, regulations, just things to pay attention to.
yeah, so what I basically focused on the test methods that they are currently used to address the rollover safety issues. So what I recommend is from these 3 tests that we have, none of those tests, I think, in my view, could replicate accurately what will happen in a real world crash. So I can have some recommendation to develop a new test that can replicate the occupant kinematics, even not in the full scale test, maybe in a component test, to better represent the occupant response that occur in a real world crash. So the recommendation could be designing a new safety test or like a component level test. And also,
do you have an idea what that might look like?
Yes, like we did some component tests using the side airbag. It was an experimental test that we did, and I don't have a video here. But we for example, tried to have a side airbag for installing the sidewall just to see how it will develop the the injuries. But I don't have like a slide that shows like what would be the exact component test that we could do for that. So if I can understand it, and also of course, as you said, 2-point versus 3-point versus unbelted. This is very clear to look at it. The other thing is in all of, especially the T-table test, that is the most widely used test. The recommendation is if you want to if you want to assess the injury outcome, you can't use the T-table test because it will not replicate and represent the occupant response as we saw from the experimental numerical analysis.
Reza, I also feel that the window issue is a pretty clear-cut recommendation that I can see. Could you comment on that?
Oh yeah, definitely. So the type of the windows that we use nowadays, people most manufacturers use this tempered glass, which will shatter after the first impact in most of the cases. So the other thing it would be how the glass by itself, we probably can use the laminated glass, or even the position of the side window can be changed from like the level that we have in most of the buses, or from the distance between the seats. So these two can probably significantly change the risk of the injuries. Yeah. So I hope.
Okay, thank you.
Oh, no problem.
Reza, I think Dr. Clark made 2 very good recommendations in highlighting the high-level contributions in the introduction of your dissertation, either in abstract or at the end of the introduction.
Yeah, I will add that.
Because the challenge that I see is that you have a lot of different aspects that it's kind of hard to see the high-level contributions immediately. So you can sort of spell them out. And recommendations, you can have a few bullet points at the end in the conclusion also.
Yes, sure.
Can I go next?
Yeah.
Yeah, well, good presentation, Mr. Said.
Thank you.
Yeah, and to follow up on Dr. Clark's point there, seems you have a lot of contribution, but again, your research was multifaceted. You have a lot of things on experimental study that you even published, on finite element analysis and accident reconstruction. Can you foresee maybe your contribution being said or documented by you know, those different themes?
Sorry, can you repeat your question?
Yeah, I mean, your research is multifaceted. There's a lot of things,
Yes.
different area, right? So it's likely, and I'm pretty sure you have contribution practically in all of them, in experimental study that you did, and you even published in that, finite element analysis, accident reconstruction.
Mhm.
So maybe you can categorize those contributions you made to the body of knowledge by those themes, by those sections.
Oh yeah, absolutely. You want me to add it in my dissertation?
I'm not sure if that's what I'm asking, but I don't know. I'm just following up on the recommendations that were made, you know, just.
I think that makes a lot of sense. There are even like the ACI journals, they have a specific recommendation. What is the contribution of this work? So I think it's good for you to kind of think in terms of the kind of high level executive summary in terms of contributions of the work.
Yeah. So I still don't know, is it like more of a question or is it just a recommendation?
I think it's a recommendation.
Okay.
Yeah, it's a recommendation.
Okay, sure. Yeah.
Just a recommendation. But, you know, for whatever it's worth, and again, you are the star of the show there, so you can take it for whatever it's worth, and you can think about how you can improve that going forward. But that's has already been said. I just have only one question. In your recommendations, you said your study was more of a deterministic, and you said you'd like to see a more stochastic study of these things. I need a little bit of clarification there, in the sense that if somebody was doing a stochastic study along the lines of your study, how will that be set up? What are the variables? What are the experimental setup and other things? And what kind of results do you think you'll get that are different from yours? Because that's a major recommendation you are making there, saying mine was deterministic, but I would like to see a stochastic study.
Yeah, that's, I think, one of the things that I will probably look at it after my graduation, probably as a postdoc. Yeah, so what the analysis that I did, so we have, like, we don't have a range for parameters. So we do have like different points, like two frictions, two like with and without side window, or like different distance between like 2 or 3 distances, or different test number. So what I mean by stochastic is we can select a range of for each parameter. So for example, for the height, we could have a range from 0 to like 1 meter for different type of tests. Like for example, with the T-table test, we have a range for the parameter for the height. We have the range for even the characteristics, for example, the material characteristic of the side window. We have the range for the position of the ATD, and then we will not have the results as a point. It's kind of like a cloud that we have. So we will see, we can do some sensitivity, how these parameters can affect the results. Before, because we had finite element simulation was computationally expensive, it was very hard to do like sensitivity study or stochastic analysis using these high fidelity models. But nowadays, I've seen some papers that they did stochastic. So even selecting the parameters is a random process. So they select different random parameters with a certain range that comes from real world data or comes from the experiment, and then do the analysis instead of using only one point to conduct their simulations. So my results is based on, for example, 10 simulation, but for stochastic analysis, we probably will have 100 simulation.
I feel like what you're explaining is more like a design of experiment with multi-level.
Well, yes, one part of it is similar to design of the experiment too. Yes.
Yeah, multi-level rather than stochastic. When you use stochastic, you bring issues of probabilities.
Yes.
Which you know, it's a little bit
Yeah.
different, but it's all good. It's all good.
Yeah.
All right. Thank you. That's all for me.
Thank
Good presentation. I enjoyed it.
Thank you so much. So
Maxim, do you have any questions or comments?
Yes, just a couple quick remarks. So first of all, thank you for presentation. Right, I think it was good, thorough presentation. I don't have any technical questions. I think I asked you most of the technical questions in your previous progress presentations. I have like a more generic question. What are your plans after graduation? Do you plan to continue your career in academia, or are you looking for positions in industry?
well, I will first start as a postdoc with Dr. Jung. So I will stay here in the school at least for a year based on the opportunity that Dr. Jung gave me. But after that, honestly, I'm not like 100% clear that I will go to industry or academy. I will probably try both to see which way I will end up. So I will not eliminate any options for myself.
Okay, well, that's good because right now job market is going to be probably depressed somewhat because of coronavirus, but after some time, after maybe your postdoc position situation is going to become more stable,
Yeah, hopefully.
and hopefully there will be more opportunities for you.
Yeah.
All right, good luck.
Oh, thank you. Thank you so much.
All right, Reza, we need to have a closed room discussion. Can you go out and then come back in maybe 5 minutes? You need to just
because I am the
leave.
host, so I don't know if I can move.
I think you can leave
Okay.
without kicking other people out.
Yeah, go to waiting room. Put yourself in a waiting room.
I think Reza can make Dr. Jung as a co-host.
Okay.
There is a way, and